All right. So let's start talking about compositions. Compositions of linear transformations and inverse of a linear transformation is the same as what you had in pre-calculus when you talked about functions. Okay. So here you have a function f from, let's make it from R to R, and you have a function g from R to R. Then you can ask if composition G or G composition F. Also, when your function F is 1-to-1, we can talk about the inverse of your function. Okay. So, for example, when you talked, if you remember, when you talked about, let's say here, y equals tangent x, and then you talked about, let's say this is f of x, and here when you talk about g of x equals sine x, so then you talked about f composite g of x, and that is tangent of sine x. Correct? That's what we mean by the composition. That's what we mean by the composition. Okay? Now, if you want to talk about f inverse, so that is what? That is what you called tangent inverse. So how do you talk about tangent inverse? Well, you make the domain of f from, do you remember that? It was from negative pi over 2 to pi over 2 to negative infinity, infinity. And this is tangent. So here, this is tangent. Now, when you talk tangent inverse, you make the range domain, you make the domain range, and you talk about tangent inverse of whatever you want. You talk about tangent. By the way, what's tangent inverse of 1? Do you remember that from calculus 1? What is tangent inverse of 1? Are you with me, guys? Okay, pi over 2, pi 45. Muhammad, is it pi over 2 or pi over 4? Smith, pi over 4. Yes, pi over 4. Okay, pi over 4. Yes, so that is something you had in pre-calculus and calculus 1. So the composition of functions and one-to-one functions and the inverse of an invertible function. Okay, so basically here you need your function to be one-to-one. You need your function to be one-to-one. And in that case, you can talk about the inverse. The inverse will be this, and here it will be this. So this is tangent x, this is tangent inverse of x. And you know here, this is symmetric or mirrored around y equals x. All right, so this is calculus 1. I'm quickly here reminding you of that. So now let's start talking about linear algebra. In linear algebra, we are talking about the same thing, but instead of functions, we are talking about linear transformations. Same for linear transformations. Okay, same for linear transformations. So you have two linear transformations, and you want to talk about, for example, the composition of two linear transformations. You want to talk about the inverse of an invertible linear transformation. Okay, so let's start here by two linear transformations. Let's take those two linear transformations. You have this one and you have this one. This is defined by this formula and this is defined by this formula. So we have here two linear transformations, one of them from P2 to P2 and one of them from P2 to P3. Okay, and this is the formula of T1, this is the formula of T2. Let me ask you, what is T of T1 of x squared minus x? What is T1 of x squared minus x? Any of you? X squared minus x minus 1. Iyad, x squared minus x minus 1. Are you sure? Iyad, are you sure? By the way, if any of you like to talk instead of writing, it's fine. You can talk if you want to. Just raise your hand and talk. X squared minus 3x. Smith, are you sure? Aha, Iyad, yes, you got it now. Iyad, yes. Now this is going to be x minus 1 squared minus x minus 1. That is correct, yeah. So now you got it. What about T2 of x squared minus x? Any of you like to answer this? Or because it's easy, I'm going to answer. Okay, this is x1 plus x plus 1 multiplied by x squared minus x. Okay, so now we understand the job of T1, we understand the job of T2. The question is, what about the composition? T2 composite T1 of 1 minus 5x squared. Well, it is like functions in pre-calculus. You substitute this inside this. So here you let the first machine do its job, and the output of the first machine you put it in the second machine. So what do you get here? You get T2 of T1 1 minus 5x squared. What is that? That's 1 minus 5x minus 1 squared. And now you substitute this in T2. So what do you get? You get x plus 1 multiplied by 1 minus 5x minus 1 squared. Is it clear? Is it clear, guys? All right, good. Mu'tasim, Iyad, okay, all of you. So what about the others? Let me make sure here the others are with me. Noura, yes. Ashok, yes. Okay. Rashid, are you with me? Islam, yes. Rashid, Tala, are you with me? All right, okay. Okay, Rashid with me, Tala with me. Okay, good. So all of you are with me. Well, sometimes I check because sometimes I know, guys, maybe you turn the session on and you go to eat or cook or do something. So I have to keep asking and make sure that you are with me. Okay, Ola with me. All right, good. Okay, Hassan with me. All right. Okay, good. So here, when it comes to composition of functions, that's very easy. So it's a piece of cake, okay? So I should not spend too much time on it. All right. Now, here is my question. Let's go back to my example here. T1, is T1 invertible? Can we talk about the inverse of T1 can we talk about T1 inverse? Yes, because one-to-one function. Okay, so if it is one-to-one, yes. If T1 is one-to-one, then yes. Now the question is T one-to-one? Is T1 one-to-one? So now the first question took us to a second question. Is the linear transformation T1 one-to-one? Sid, how to check whether it is one-to-one or not? The determinant of what? Mu'tasim, you're saying the determinant. The determinant of what? Is T one-to-one? Find the kernel. Yes, yes, find the kernel. Kernel T1. Dimension of kernel. So find the kernel. What's the kernel? What is the kernel here? Let me give you a few seconds. Find the kernel, please. What's the kernel? Please write it down. If you have a piece of paper, get a piece of paper in front of you and write it down, because I want to make sure you can write the kernel correct. Write the kernel and see what is the kernel. Don't rush to give me the final answer. Please write down the steps. Mu'tasim? Kernel of T1. Kernel of T1. Please write it on a piece of paper and see whether you can write it correct or not. If you want me to go up so you can see it, I can go up. Here it is. Here is T1. And this is P2. This is T1 from P2 to P2. All right. So what is the kernel? The kernel is going to be all polynomials of degree at most 2 such that a x minus 1, or let me write it here, a x minus 1 squared plus b x minus 1 plus c is 0. This is the kernel. All polynomials of degree at most 2 that will satisfy this. Now, what is this? If you want this to happen, it means what? From here, you can see a has to be 0. And from here, you can see b has to be 0. And c has to be 0. In case you don't see that, you can unfold those. Okay? Saif, we are waiting for you, Saif. Where are you? Okay, so a equals 0, b equals 0, c equals 0. And in this case, it means this is the 0 polynomial, and it means the kernel is the trivial subspace. All right, okay. So this is your kernel. All right, okay, Saif. All right. So the kernel is the 0 subspace. Is it clear? Is it clear why? Okay? All right. So that is the kernel. So here, hence, T1 is 1 to 1. T1 is 1 to 1. Okay? Because the kernel is the trivial subspace. Now, my next question. My next question, is T1 onto? Anybody like to answer that? I'm waiting for you guys. Maitha, is T1 onto here? Or Fatima or Faisal? Rashid, Raya, Saif, Salama. All right. If you tell me yes, okay, yes, yes, yes. Okay, so yes. And you know what follows yes? Why? Explain, justify. So why it is yes? You can speak. If any of you like to speak, you can speak. Why it is yes? It is onto. Why it is onto? Rank T1 equals dimension. Very good, Smith. Yes. Yes. Because rank T1 is the dimension, using the theorem, rank plus nullity equals the dimension of the domain. So rank T1 is going to be the dimension of P3, 3 minus 0, which is 3. So here, so range T1 is P2. So T1 covers all P2. So yes, it is onto because T1 covers all of P2. The rank is 3. Okay, is it clear? So now, hence, T1 is onto. Okay, now it is 1-to-1 and it is onto, which means I can ask you here, find T1 inverse. It is 1-to-1, it is onto, so it's invertible. So it means T1 inverse is going to be from P2 to P2. And my question now, find a formula for this. What's the formula of T1 inverse? If you go to T1 here, here is T1. Again, here is T1. What is the formula for T1 inverse? T1 inverse of Qx is going to be what? Yes, yeah, Qx plus 1. It is going to be the opposite of T1. In T1, you subtract, you shift 1 unit to minus 1. So you shift 1 unit to the right. So here you shift 1 unit to the left. Okay, so if you are not sure, all you need is to do this. T1 composite, T1 inverse of Qx. This is going to be T1 of Qx plus 1. And what is this? This is Qx. So that is how you can make sure T1 composite, T1 inverse is going to be the identity. You see that? Okay. Are you following me, guys? Any question? All right. Okay, good. All right, good, very good. So let me give you another example. So this one, it was 1-to-1, it was onto, so it is invertible. We found the inverse. Let's take another one. All right, here you go. So this is question. You can call it question 2, question 3, whatever it is. You have this linear transformation from P2 to P2, and the question here says find whether Px is in the range or not. Okay, This is the range here. Well, I can ask here more questions. I can ask here, is T 1 to 1? I can ask you, is T onto? I can ask you, can you find T inverse? Okay, so basically you have a linear transformation. I can ask you all type of questions about this. 1 to 1, onto, what is the range, what is the domain, find the basis for the range, find the kernel, find the basis for the kernel, all the things that we discussed, I can ask you about them here. Okay, so let's answer those questions one by one. Okay, so the first question, determine whether this polynomial belongs to the range or not. Guys, please write this linear transformation in front of you on a piece of paper, so when I scroll down you keep seeing it. Okay, so please write it on a piece of paper, because it's difficult for me to keep coming back and forth. Okay, all right, now the first question, is this polynomial in the range? How do you answer this question? No, it is not in the range. No. Why no? Iyad, why no? Smith, why no? Please feel free to speak if you have a microphone. Why no? A equals to B equals from the transformation. Okay, so A is 2 and B is 6. A minus 2B not equals. Aha, yeah. Okay, good. So what you need to do here, you need to understand the range. So here, solution 1, try to understand the range. Try to understand the range. What is the range? Range T is all polynomials that are taking this form, ax squared plus a minus 2b x plus b, such that a, b, and r. That is the range, correct? Am I correct, Nora, Ola, Raya? Am I correct? That is the range. And that is, I can write it as a into x squared minus plus x minus or plus b into 1 minus 2x, such that a, b belongs to r. And this I can write it as a span of x squared plus x, and here 1 minus 2x. Think about what you see here. Is that clear? Do you agree with me? That is the range. It is the span of those two vectors, x squared plus x and 1 minus 2x. Yes, Zaid, we are trying to understand the range here. What is the range? What is the range of T? This is the range of T. Correct? That is the range of T. Okay, now all you need here, Zaid, is try to understand this range. How do you try to understand it? Well, you see, the range is a subspace. So you need to understand this subspace. Well, this subspace here, if you just toy with it, you write it in this way: a into x squared plus x, and b into 1 minus 2x. And that is the span of those two vectors. So here you can see bases for the range. So here you can see this is your basis for the range, or a basis for the range, correct? Zaid, is it more clear now? All right. So now we understand the range. The range is going to be spanned by those two linearly independent vectors. Okay? So now let's go back to our question. Our question says, is this polynomial px equals 2x squared minus 4x plus 6 in range T? So what is the question now? The question is exactly similar to one of the questions you had in your quiz number 4. Is, in other words, is px in span x squared plus x 1 minus 2x? Am I correct? Look at it. That's the question. Is this polynomial in the span of x squared plus x 1 minus 2x? What do you think, guys? Well, Iyad answered the question already. Iyad said the following. Iyad said, well, if this is the case, this means 2x squared minus 4x plus 6 has to be C1 x squared plus x plus C2 into 1 minus 2x. And if you have this, this means C2 has to be 6 and C1 has to be 2, and you have C1 minus 2C2 has to be negative 4. But what is C1? This is 2 minus 12 is negative 4. This is wrong, not possible. Correct? So this is not possible. It is not possible to get 2x squared minus 4x plus 6 as a linear combination of this and this. Okay? Are you with me, guys? Ola, are you with me? Okay, Iyad and Smith with me. Okay, Ola. Okay, Salama. So, all right. So, is it clear now? So now we can say hence P of x does not belong to range T. So now you can go back and answer my question here. Where was that? This one, question number 1, we answered that. No. Find a basis for RT. Did we answer number 2? This one, number 2, did we answer that? Yes, we found a basis for RT. Yes, Tala, correct. Now, is T 1 to 1? Well, did we answer that? Is T 1 to 1? Okay, is T onto? Let me jump to number 4. Is T onto? We answered that. Is T onto? No. Yes. No. Why it is no? Because we found the range. The range does not cover the whole codomain. It doesn't cover P2. So no. So now we need to answer, is T 1 to 1? Number 3. Let's answer number 3. Is T 1 to 1? I'm going to give you 1 minute. Can you answer that? So now, is T 1 to 1? I'm going to give you 1 minute, please. All of you answer this question. And after 1 minute, I'm going to just select some names. We cannot. Yeah, I'm asking you, is T 1 to 1? Oh, yes, you cannot find the inverse. Yeah, of course, because it's not 1 to 1, because it's not onto, and you are going to see whether it's 1 to 1 or not, and after that we talk about the inverse. No, it is not. Well, let's not talk about the inverse now, because the range doesn't include all. I'm not asking you about the inverse. We are going to come to that. I'm asking you about, is T 1 to 1? Is T 1 to 1? This is my question. Islam, yes. Smith, yes. Muhammad, yes. Why, yes. Why it is 1 to 1? Ali, yes. All of you saying, yes, it is 1 to 1. Why? Why it is 1 to 1? Because the kernel is 0. Ali, is the kernel 0? Islam, is the kernel? What is the kernel? Can you find the kernel? So here now the question becomes, find the kernel. That is the question. Tala, no, it is not 0. All right, some of you saying the kernel is 0, some of you saying the kernel is not 0. So think about it and try to give me the final answer. Kernel T. All right, did you get it? What's kernel T? Kernel T is going to be all polynomials Px in the domain such that when you substitute, you get 0. And that is going to be all polynomials ax squared plus bx plus c such that when you substitute, what do you get? You get ax squared plus a minus 2bx plus b equals 0. Now, what is this? You need to understand this. What is this? From here, b must be 0, a must be 0. So, what do you get? A is 0, b is 0. What about c? C is free. C can be anything. And what is that? So what is the kernel, guys? Ali, what is the kernel? Muhammad, Islam, Smith, what's the kernel? The kernel is not 1. The kernel is the span of 1. Yes, Siyad. Mu'tasim, look here, it's very important. The kernel is the span of this. Span of this. The nullity is 1. Don't mix between the nullity and the kernel. Look, this question here. The nullity is 1, but the kernel is a span of 1. Yes. So, you know, guys, in such this case, I can write a multiple choice question. I can write a multiple choice question in which I write the kernel is 1, the kernel is a span of 1. So you need to know what is the correct answer. The kernel, if I ask you about the kernel is a span of 1. What is the nullity? The nullity is 1. So you have the kernel in front of you. Hence, T is not one-to-one. It is not one-to-one. Now you can say, therefore, we cannot talk about T inverse. We cannot talk about T inverse. Okay, any question about this? Any question about this one, this example? It is not onto, it is not one-to-one. We found the kernel, we found everything. Okay, all right, so now we are ready to move on and talk about the matrix of a linear transformation, or matrices. Matrices for linear transformation. Okay, so if I go back here to the example that I gave you, and here when I say T from P2 to P2 defined by T Px equals a x squared plus a minus 2bx plus b. If you look at this, this is a linear transformation. We understand everything about it. Now, my question to you, can you think about T as a matrix? This linear transformation, can we think about it as a matrix? Let's see, those who, Ali, yes, okay. Those who watched the recorded video, what do you think? How many of you watched the recorded video? Mu'tasim, yes. All right, Smith, yes. Yes. Yes, we can think about this as a matrix. Any linear transformation over a finite dimensional vector space can be represented by a matrix. So here, yes, we can think about T as a matrix. How? How do we think about this as a matrix? Well, here is the idea. The idea here, step number one, take a basis for your domain. So take a basis for the domain. You know the domain here. The domain is P2. Take a basis for P2. Which basis would you take? Well, make it easy. Take the standard basis. You can take any basis, but here you can make it as easy as possible. Take the standard basis. So we took a basis for the domain. 2, take a basis for the range or the codomain. Let's call it P prime. I want to take it the same, standard basis. Okay? Now, step number 3. Find the coordinate vector of t of 1 with respect to b prime, t of x with respect to b prime, t of x squared with respect to b prime. Again, what are those? Look here, t of 1, here is 1. So you see the image of 1 and you find the coordinate vector with respect to the basis of the range or the basis of the codomain. So here, when you do that, what do you get? You get, what is t of 1? Please substitute in the formula. What is of 1? This is still the same t. Yes, it's the same t. I'm talking about the same t here. The same t that I used before. Here, let me go up so you can see it. Where was it? Here, it's the same t here. It is the same t. Yes, what is t of 1? Okay, yeah, it's 0. All right. What about the others? Can you confirm? Ashok, what is t of 1? 0, 0. All right, good. So all of you agree it is 0. Now, what is t of x? All right, always Iyad gets the answer right away. Okay, what about the others? Do you agree with him? All right. Abdullah, yes. Ali, yes. Okay, so all of you agree with Iyad here, negative 2x plus 1? Yes. All right, Noura, yes. Ali, yes. Okay. Now, what about this? Tx squared. What's the coordinate vector of Tx squared? What is Tx squared? Tx squared. Ali, x squared. Okay, good, Ali. So to this time you got it before Iyad. Okay, so that is x squared. So now, what is the coordinate vector here? So the coordinate vector of 0 with respect to p prime. Still we are using p prime, the same basis, 1x x squared. So what is this? This is going to be, what's the coordinate vector? Can someone give me the coordinate vector here? Ali, okay, you got it, Ali. So Ali now is becoming faster than Iyad. All right. So 0, 0, 0. The coordinate vector is 0, 0. What about the second coordinate vector here? Sir, shouldn't the last one be x squared plus x? The last one, let's double check. X squared. You're absolutely right, Iyad. A is 1, so this is x squared plus x. Thank you very much. Yes, you are right. Because A is 1, so when you substitute, you get ax squared plus ax. So yes, that is correct. Thank you, Iyad. That's correct. So now, what is the coordinate vector here? 1, negative 2, 0. We have to follow the same order, I'll show. 0, negative 2, 1. No, it is 1, negative 2, 0. You have to follow the order. Look, the order is 1, x squared. So the 0 is coming down. All right, good. Okay. Okay, now what about this one? 0, 1, 1. All right, so now we got the answer. Hence, T, the matrix that we are looking for, the matrix, this is number 4. For the matrix is, this is how we write it. T, the matrix P prime P is you take the coordinate vectors and put them as columns. That is your matrix. This matrix will do the same job as the formula that you have. If you don't believe me, I can clarify it further. Here, when you take P of X and you send that into TPX, instead of this, I can write the coordinate vector of Px with respect to P. And now I can multiply this coordinate vector by the matrix of T to get matrix of T P prime P multiplied by Px with respect to B. And from this, I get the coordinate vector of TPX with respect to B prime. Now this, I use it to get this. Okay? So guys, here is what happens in this diagram. You can see what happens. Instead of going straight from here to here, you can go to this, then go to this, then go to this. Instead of going from your home to the supermarket through a direct route, you can go visit your friend, and after your friend, you can continue and go to the supermarket and come back home. Okay? So basically, you take a different route, but you can get the same thing. I have 3 minutes. Let me clarify this by an example. Okay? Take your Px to be any example. For example, take your Px to be, take any polynomial you want. Can any of you give me a polynomial here? Let's see, Noura, can you take any polynomial you want? Whatever polynomial in P2, take anyone. Abdullah, Noura, any of you can take, let's see, who's going to give me first a polynomial? Let's see, Ula, Raya, Rashid, Saif, Salama, Sheikha. X squared plus 2x plus 1. Okay, Tala, thank you. X squared plus 2x plus 1. All right. So now, so I took the first one, the first example you gave me. It was given by Tala. So now I can write the coordinate vector of this with respect to B. What is the coordinate vector? 1, 2, 1. Correct? All of you agree with me? Yes. All right, good. So now the question is, what is T of x squared plus 2x plus 1? Now, we don't want to do it using the formula. We want to do it using the matrix. Do it using the matrix. How? This is how we do it. I need to go back here. Please, guys, help me to remember the matrix. What is the matrix? Here it is. Here is the matrix. 0, 0, 0, 1, negative 1. Okay, please help me to get it. 0, 0, 0, and then here 0, 1, 1, and here 0, no, it was 1, negative 2, 0. Am I correct? 1, negative 2, 0. Am I correct? 1, negative 2, 0. All right, thank you. 1, negative 2, 0. So this is the matrix. Now, we let this matrix act on the coordinate vector of Px, which is 1, 2, 1. From this, what do we get? Multiply. What do you get? You get 2. You get -4 plus 1, -3, and you get 1. Now, translate this. This is the coordinate vector of your answer. So this is going to be TPX, the coordinate vector with respect to P prime. Now, translate this. What do you get? You get TPX equals, this is the coordinate vector of what? This is the coordinate vector of this. Am I correct? 2 minus 3x plus x squared. Yes, okay. Now, if you do it using the formula, do it using the formula. You should get same answer. And that is the end of this section. So basically, for each linear transformation over a finite dimensional field, you can find a matrix from the coordinate vectors, and the matrix will help you to do the same job. Okay? And you need to be able to travel back and forth between the linear transformation, its formula, and between the matrix representation. Any question? Will they tell us whether to use the matrix or the formula? Well, you should be able to use both. It depends on the question. When you do the exercises, you will find how to handle that. We can ask you all type of questions. Find the matrix, use the formula. Okay? The matrix will tell you the same thing as the formula. In fact, if the matrix is invertible, the linear transformation is invertible. The matrix will tell you everything. Okay? So thank you very much, guys. Stay safe and have a good spring break. We meet after the spring break. After the spring break, I'll give you the chance to ask questions. Also, I may give you, I can make an office hour where I can help you in case you need help during the spring break. So we will be in touch by email. Thank you, Abdullah. Have a good day, and try to practice more exercises.